Moving ahead, the intended audience of this course is basically as broad as the applicability of finite elements. So, finite elements is a multi-physics tool, and so you could be an undergraduate or graduate student from STEM fields, or engineers or scientists from STEM fields. So long as you are fulfilling the requirements, I think this course will really help you. A bit about myself: I am Jaydeep. I am basically a chemical engineer, and you could think of me as a researcher and an entrepreneur. And this is Amnium Technologies, my own company, which I have founded after my PhD. That was about 4 years back. Primarily, I work in the field of nanotechnology. So here there is no specific CFD solver available for nanotechnology, because you are also so when you are creating nanoparticles. So primarily my job is to develop technologies for synthesizing nanoparticles. And for nanosynthesis, you are really dealing with continuum phenomena, you're dealing with mesoscopic phenomena, and you're also dealing with thermodynamic phenomena. So you really do not have a single CFD solver. So you have to code from scratch many times, and you have to do a lot of experiments as well. You have to do some approximations. So a lot of engineering and a lot of fun. And I am happy to say that I have worked with my clients and put multiple FDA approved products on the market shelf. Currently there are 4 products on the market shelf, and many more are on the way. So this is one technology which we are developing right now, and I cannot really reveal a lot of details due to IP constraints. But this is basically a miniaturized reactor in which we are preparing nanoparticles from a drug or pharmaceutical kind of application point of view. And really we have used finite elements intensively in this design, and I can tell you that the predictions from finite elements are good, and we have been able to cut short a lot of our experimental load by use of those predictions. So this is me. I am a reaction engineer, a chemical engineer, somebody who is working on the interfaces of material science, nanotechnology, and chemical engineering. And this is the field where I look for opportunity. This is what pays my bills. And then this is again me, and this is me not from an opportunity point of view, but from a passion point of view. So this image is of me just after my PhD. The first thing that I did after my PhD was over is I went to a school and I started doing science outreach. So I did some nice nanotechnology related experiments, because I really enjoy this. I enjoy working with students, and even now in my company I am always having some industry academia collaborations, mentoring students. Around 40 to 50 students I have directly mentored by now, and 30 of them are really close mentoring, you could say. So I really enjoyed this activity, and when I started doing this activity, a well-wisher told me, like, don't waste your time in academics, just go to the industry, and that will give you a very good experience. You should solve real problems, industrial problems. You should supply material to the industry. It will make you more responsible, more effective, and so on. And it was really good advice, I would say, and that is why I founded this company actually. And it was a good advice because we were very new at that time with what we came up. There weren't a lot of competitors, and this really helped us reach out to a lot of customers without doing a lot of marketing, and that really benefited us. So really the thing that I learned is that you need both passion and opportunity. You have to run both of those tracks parallelly, right? So passion takes care of your sleep, and opportunity takes care of your stomach. Okay, so that brings me to the next point, is that why are we really interested in upskilling or in educating ourselves? So we are looking at the opportunities, right? Because in any field there are going to be sunset fields and there are going to be sunrise fields. So you could look at a factory, and it is there is a lot of capital flowing through the factory. There's a lot of money flowing through it, right? So capital rotation is not so One way to look at it is that capital rotation is a necessary condition for wealth creation, but it is not a sufficient condition, which means that you could have a lot of capital rotation, but there's not so much wealth creation. And you typically see this in sunrise sectors, where the sector has really grown very. You see this in sunset sectors, because the sector has grown really big because of the service it has provided for the last few decades. And so there is a lot of capital rotating inside the sector, but it's saturated, right? So right now you could see there are so many engineers who have got higher education and they are not able to get good jobs, and that is because the field is saturated. So we have to look at fields which are sunrise fields, and typically those are fields where the companies are really pushing, right? So those are the fields at the interfaces where lot of multi-physics is coming in, even social entrepreneurship is coming in, politics is coming in, business, like the hardcore, the hardcore capital rotation sort of business, money lenders and investors, and all of the chaos is there, right? And those are the fields where you have good employment, you get good growth, right? And for those fields, really we need to understand the script, right? So we need script writers for those fields. We don't need language writers. So what do I mean by that? You can look at DeepSeek, for example. So there was a lot of surprise over how DeepSeek could match OpenAI, because OpenAI had a lot of capital. They were rotating a lot of capital. So whether DeepSeek had access to GPUs or not, the kind of GPUs which OpenAI had access to, we can definitely say that they were good at the script, and the script was mathematics. So any science field or any technological field, the script is mathematics. So if you're good at the script, you can basically break the opportunity which lies at the interface. So that's really the crux of even finite elements, because as I mentioned, finite elements can combine with so many things in the computer-aided engineering landscape. So for example, if you are an engineer who is a CFD engineer and you have learned your finite volumes really well, and now somebody tells you of this really interesting problem of a cell wall, modeling a cell wall, and it has a lot of scope in the biopharma sector, for example. And you're saying like, okay, I have learned the finite volumes, I have learned turbulence, which is really satisfying. It's a very complex problem, but there are so many people, it's a saturated field. Okay, so there is a lot of opportunity there, yes, but it is a saturated field. So the supply demand dynamics are such that there are many people, there are many experts in this field. And then you could be a microbiologist and you're not really interested in how the simulation is running, or how these predictions can improve your experiments, cut down the load of your experiments, and so on. So along comes a guy who is not really super smart or super talented, but he just acts as an interlocutor and brings those two fields together. Okay, so that guy is going to reap all of the opportunity. Okay, so the opportunity always lies at the interfaces, and you can really hire experts from both sides, and the interface is what is making the money, right? And finite elements is good because it allows you to hop from one field to another. You could be in microbiology, geology, or medical, or you're designing drones. Finite elements is good for everybody because it's a multi-physics tool, right? So as educators, sometimes we fail at this. We fail at pointing out opportunities to our students. And that is why you have so many engineers who are jobless. That is because we as educators have failed to point them to the right kind of opportunities, right? So instead of playing just the capital rotation game, we have to also encourage the students towards wealth creation.